Alright, so the paper I'm going to run through today is Physics. This is paper 6, Alternative to the Practical, for October-November 2018. And this is variant 6.1, so it's code 062561. And this, of course, is the Cambridge International Examinations Board, which is for the Cambridge IGCSE. Alright, let's begin.
Go! Well, let's rock.
Question number 1. A student is determining the spring constant K of a spring by two methods. Figure 1.2 shows how the apparatus is used. Method 1, on figure 1.1, measure the unstretched length L0 of the spring in millimeters. Okay, so what you're going to have to do here is pull out your ruler and physically measure the spring on the page of your exam. And I want you to measure that section here, L0, so between this line and this line. Now it's clearly marked, so you should be able to get a good measurement. The actual measurement that they're looking for is 22 millimeters. And again, as I've said in the other exam papers, if you're measuring this on one you've printed out at home, or one that's been printed out for you on A4 paper or on letter size paper, you may well get a different answer. And the reason is because as it's been printed out, it will have resized it to fit the paper. So don't worry if your answer's out by a couple of millimeters. I printed mine on letter size paper, and this size I got was actually 20 millimeters, and I measured it pretty well. It's probably a good idea, as you're running through these practice exams, to make sure that you've got this measurement right at the start, so you can get the next few marks without worrying about it. So 22 millimeters is the number they wanted. Part B, the student attaches the spring to the clamp as shown in figure 1.2. He hangs a 300-gram mass on the spring. Right, okay. He measures the new length of the spring. Excellent, this one has been done for us. Calculate the extension E of the spring using the equation E equals L minus L naught. Alright, nice and straightforward. That's E equals 53 millimeters minus 22 millimeters, which should give you 31 millimeters. The units are already there, but always check. 2. Calculate a value for the spring constant K using the equation K equals F over E. Right. Okay, so let's do this and let's put the information in that we have. The value of F is 3.0 newtons. The value for the extension E you've just calculated is 31 millimeters. And that gives you a value of 0.0968 newtons per millimeter. So let's just write that in. Method 2. The student pulls the mass down a short distance and releases it so that it oscillates up and down. Figure 1.3 shows the time taken, T, for 10 complete oscillations. Record the time taken T for the oscillations. Alright, that's just asking you to write down the value that you're seeing for the time over here. So 3.46. Again, look, there's no units. Make sure you write them in. Very important. Now this is for 10 complete oscillations, and that's important because now in part 2.1 it's asking you to calculate the time T for one oscillation. So what you want to do, T, well, if that's the time for 10 oscillations, and you just divide it by 10. So 3.46 seconds divided by 10 will give you 0.346 seconds. And again, remember your units. Part 2, calculate T squared. Right, so that's 0.346 squared. And that gives us a value of 0.1197. We wouldn't write 4 significant figures, it's too many. So we'd actually just change that. It would be 0.12. You could put 0.120, that'd be fine as well. But 4 is just too many. Part 3. Calculate the spring constant K using the equation K equals 0.040 m divided by T squared, where m is 0.3 kilograms. Okay, so write down your little calculation. We have K equals 0.040, which we're given, multiplied by 0.3 kilograms, divided by T squared that we just calculated is 0.120. There we are. And if you put that into the calculator, you get the value 0.1 1. 0.1 newtons per millimetre. Excellent. Let's come on to the next one. D. State and explain whether your two values for K are within the limits of experimental accuracy. Ooh, interesting. Normally it asks you if they're close enough or the same or something, and you would say, yes, within the limits of experimental accuracy. Sometimes, though, they throw the limits of experimental accuracy statement into the question. So what you need to do then is explain what the limits of experimental accuracy means. Kind of say they're very close. So let's say that. We'd start off with our statement, yes, the two values for K are the same. For our explanation, what we might want to do is say within the limits of experimental accuracy, as the results are very close to each other. There we go. And the reason we're saying that, of course, is because the first value we calculated, we got K equals 0.0968. And that was newtons per millimetre. The second value that we calculated was 0.1 newtons per millimetre. And those values are very close. That's why we can say they're the same. If they were very different, then we would say no, they're not the same. They're within the limits of experimental accuracy. These results are different if they were separated, if they were very largely separated. E. A student states that repeating method 1 with different masses would improve the reliability of the values obtained for K. Suggest additional values for the mass M that you would use when repeating the experiment to improve reliability. Alright, well, if we look at the experiment itself, the mass they used was 300 grams. That seems quite a reasonable mass, so I guess if I wanted to improve it, I'd probably use, say, 100 grams, 200 grams, and let's run a 400 grams. I wouldn't want to use a mass that's too small, because the results might not be as noticeable. And I wouldn't want to use a mass that's too big, say for example 20 kilograms or 3 tons or something like that, because it doesn't get more accurate. There's a point where you break the spring. You know that the spring can take 300 grams without any problems. It's asking you for 3 weights that would be appropriate. They seem pretty appropriate. If you want to do 50 grams, 150, 250, that would be fine as well. Those sort of numbers are what you're looking at. You wouldn't want to go smaller than 50 grams. And I would guess at this rate you probably wouldn't want to go bigger than half a kilogram, 500 grams. I think that would be your upper limit there. Excellent. Let's move on to the next question. Question 2. A student is determining the resistance of a piece of wire. Figure 2.1 shows the circuit she uses. There we go, got a nice little circuit showing up. A. Record the current I in the circuit as shown on the ammeter in figure 2.2. Alright, so let's go down to the ammeter. Figure 2.2. Right, so one on the left. Now if we look at that, this section here is 0.5, so that means that this is currently located at 0.48. And look closely, no units. So make sure you write them in. B. The student places a sliding contact C at a distance L equals 20.0 centimeters from P. The voltmeter reading is shown in figure 2.3. Record the voltmeter reading in table 2.1 for the value of L. Okay, now looking at our voltmeter, this is pretty much reading exactly 0.5 volts. So let's write that into our table. There we go, 0.5 volts. The student repeats the procedure using a bunch of different readings, and we get this table underneath. D. Plot a graph of V in volts in the y-axis against... I see that. This is why you've got to be careful not to run through questions too quickly. Complete the column headings in the table. There we are. So this was in centimeters, and this is in volts. Always go through it, always read the question carefully. Don't make those silly mistakes. Admittedly, I make them all the time, but don't feel bad if you make them, just try and watch out for them. Now D. Plot a graph of V in volts in the y-axis against L in centimeters in the x-axis. Start both axes at the origin 0, 0. So we've got volts against length. Let's see what it goes up to. Alright, volts go up to 2.4. What's probably going to be a good scale there, because it takes it all up, if possible, would be, say, 5 squares. Each square equals 0.5 volts. That would be a good scale. And the length, probably 5 squares. Each square equals 20 centimeters. So we've got quite lucky here. There's a good set of results there. Okay, so let's do our origin, 0, 0. The x-axis is the centimeters, and we said each big square is going to be 20 centimeters. So that's 20, 40, 60, 80, 100. So each big block of 10 squares, which is a large square, is 20 centimeters. Going up on the v-axis, right, let's label that, that's L in centimeters along that axis. Going up on the y-axis, we have each big square, each set 10, is 0.5 volts. So 0.5, 1.0, 1.5, 2.0, and 2.5 volts. There we go. So let's draw in our little axis lines. And of course then we'll quickly label the y-axis. There we go. Now that's complete. What I can do is start plotting the points in. The first one is 20 and 0.5. In fact, let's just we'll plot them all in now. Right, so that's all our points plotted. Let's move on to the next part of the question. E. Determine the gradient G of the graph. Show clearly on the graph how you obtained the necessary information. Right. Let's be clear about this. Whenever you're doing a gradient of a graph, what it means is draw a triangle. Very important. So if we come up here, we're going to determine the gradient of the graph. So to get the gradient, we're going to need to draw a straight line. So to get the gradient, first things first, I've put in my best line fit. Now I'm going to want to connect that up with a triangle and label the change in x and the change in y. There we go, so I've got my change in y and change in x, and it's very clear where the numbers themselves come from. So the gradient is just a change in y divided by change in x, which of course y is voltage, change in volts divided by change in the length. That's what that actually stands for in this case, so we get 2.5 volts divided by 100 centimeters. And that gives a value of 2.5 times 10 to the negative 2. And the units, I've got volts divided by centimeters. What does that give me? Well, it gives me volts divided by centimeters. All this is about communicating where the number comes from. There we are. That's it. Let's write that in. Part 2. Calculate the resistance R of each centimetre of the wire. Use the equation R equals G times K divided by I, where K is 1 volt per centimetre and I is the recorded current in part A. Now just looking at this nice and quickly, we're going for the resistance. The units of resistance are ohms. So what that means is when I'm writing out this equation over here to do all the working out, I'm not really going to bother putting in the units in the equation itself. It's much easier just to put ohms at the end and save a whole bunch of headaches. So let's do that. R equals 2.5 times 10 to the negative 2 multiplied by K, which is 1, 1.0, and that's obviously the volts, doesn't matter, divided by the first number we measured for current, which was 0.48 amps, and that gives us a value of 0.052 ohms. There we are. Make sure that that decimal point is nice and noticeable. There we go. Well done. Let's jump on to the next one. Question 3. A student is determining the refractive index N of a material of a transparent block. Figure 3.1 shows the outline ABCD of the transparent block. Right, so part A. On figure 3.1, draw a normal NL at the centre of side AB and continue it through so it passes through side CD. So centre of side AB, draw a normal line. There we go, so that's our normal line. A little bit tricky to draw with the software, but it's up and going. Alright, so looking at draw normal NL at the centre of side AB, and we pass that through the other side of the block. Okay, now it says draw normal NL. What that means is it wants us to label it NL. So let's do that. There we go. Next one, label the point F where NL crosses AB, and then label the point G where NL crosses CD. Okay. There we go. That's both those points labelled. Part 2. Draw a line EF at an angle I equals 30 degrees to the left of the normal and above side AB. Right, we can do that. There we go, so that's our line. That's at 30 degrees. Mark the positions of two pins, P1 and P2, on line EF. I still haven't labelled that line, EF. Okay, let's label it EF, then I'll come back to the next part. F's already marked, so I'll just put big E on the other side. Right, so we're still on this one. Mark the positions of two pins, P1 and P2, on line EF, placed a suitable distance apart for this type of ray tracing experiment. Alright, there's always a good hint here. It says, you know, a suitable distance apart. If you look at the bottom of the page, they've already got a couple of pins drawn in P3, P4. That would appear to be a suitable distance apart. So as long as it's at least that size, we're doing well. So I'll put one here, and I'll put one up closer to the top, and I'll label them P1 and P2. Always remember to do this with an eraser and a pencil, all of it, because you may find yourself suddenly making some big changes. So that bit's done then. Suitable distance apart. B. The student observes the images of P1 and P2 through the side CD of the block, so the images of P1 and P2 appear behind each other. That's good. Alright. He places two pins, P3 and P4, between his eye and the block, so that P3 and P4 and the images of P1 and P2 seen through the block appear one behind the other. Okay, good. We've already seen them, they're marked, so let's just tick this as we go through it. So we don't make any silly mistakes, we don't miss sentences. The position of P3 and P4 are marked. Good, that's nice. Okay, 1. Draw a line joining the positions of P3 and P4. Continue the line until it meets the normal NL. Okay, so we have to draw a line through P3 and P4 and continue until it meets NL. Let's do that. So there we go. I've drawn that line through it now. And it continues all the way up until it meets that normal line, NL. So I'll just tick that as well. There we go, done. Next bit, label the point H where the side meets CD. Draw the line FH. Right, so I labelled that one here, and I've just drawn this line in here, that line FH. Okay, let's move on to the next bit. There we are. Take that off. Now, to measure and record the length A of the line GH. So I have to measure G to H. Okay, so you have to measure that line GH. That's between here and here. There we go. And when I did that on my diagram, I got 1.8 centimetres. You might not get 1.8, you might get 1.9, you might get 2.0. Should be about that level. If you get 5 centimetres, either you've printed it off on A3 paper or something's gone horribly wrong. Alright, so GH, I got 1.8 centimetres. And the reason it's okay why your result might not be exactly the same is because obviously we printed these papers out on different things. I've printed mine out in letter. You might have printed yours out in A4. Maybe you've got one of the original exam papers, all of which will give you slightly different numbers. Right, part 3. Measure and record the length B of the line FH. Alright, so it's asking us to measure and record this length here, between here all the way down to here. F and H. Now when I measured that, I got a length of 5.0 centimetres. And again, don't worry, as long as your measurement is close, it should be absolutely fine. There we go. Part 4. Calculate the refractive index n using the equation n equals 0.5 times b divided by a. Well, let's write that down. N equals 0.5 times b, which is 5 centimetres, divided by 1.8 centimetres. And if I do that, I get an answer of 1.39. That's 3 significant figures. Looking at the calculation, I could do it to 2 significant figures just as easily. I'll just leave it as 3. It's absolutely fine. There we go. Okay, let's look at the next part. Part C. The student repeats the procedure using a different angle of incidence, I equals 45 degrees, and gets A as 3.2 and B is 6.9. Calculate the refractive index n using the equation n equals 0.71 times b divided by a. Sure, not a problem. Let's do that now. N equals 0.71 multiplied by 6.9 centimetres divided by 3.2 centimetres. There we go, and that should give us an answer of 1.52 or 1.5. Both are absolutely fine. There we go, 1.52. Why not? Right. The student expected the two values of the refractive index obtained in this experiment to be equal. State 2 difficulties with this type of experiment that could explain any difference in the two values of n. Alright, so a lot of this is almost like the reverse of when it says, how could you make the experiment better? It's a case of looking at it and saying, okay, suppose you did the experiment, what would make it better? Okay, that's possibly what went wrong. So, number 1, difficult to get the pin vertical. Always one of the improvements is ensure the pins are vertical, that kind of thing. So, if it's difficult in getting the pins vertical. There we are. And this experiment required someone to put a block onto a piece of paper, remove the block, and then replace it. That's never going to be great. It's always going to end up at a slightly different angle. So that's going to be our second problem there. Removing and replacing the block accurately in the same position. Right, part E. A student suggests precautions to take in this experiment to obtain reliable results. Tick one box to indicate the most sensible suggestion. Oh, what an ambiguous question. The most sensible suggestion. Well, let's do a brief check. A darkened room, that's pretty sensible. Pins that are taller than the height of the block? Nobody cares. You should be using the base of the block anyway. View the base of the pins, that's sensible, yeah. View the pins with one eye closed, that's pretty much also a bit sensible there. Okay, so let's put these in order of sensible. This is not the best question, this particular bit. But let's do the best we can with it. It's always what we can do. Okay, so let's run it through. If we don't view the bases of the pins, then it doesn't matter how many eyes we're using. And it doesn't matter how dark the room is. In fact, actually, you know what? Let's look at that again. Because let's take that first one, do it in a darkened room. We're not sending a ray of light through here. What we're actually doing is viewing pins on the other side. So that's actually not a great move either. So it comes down to these two choices. The choices between view the bases of the pins and view it with one eye closed. If you're not viewing the bases of the pins, it doesn't matter how many eyes you're using. One eye closed is good, it's better, but if you don't view the bases of the pins, your results will still be rubbish. So the most important bit here is this one. Let's give that the tick. Most sensible suggestion. Oh well. Let's go on and look at the next question. Question 4. A student is investigating the relationship between the power produced by an electrical heater and the time taken to heat a beaker of water. The power of the heater is given by the equation P equals V times I, where V is the potential difference of the heater across the heater, and I is the current in the heater. Plan an experiment to investigate the relationship between the power produced by an electrical heater and the time taken to heat a beaker of water. And following apparatus is available: ammeter, voltmeter, 0 to 12 volt power supply, beaker, heater, thermometer, stopwatch. That's a pretty good set of equipment for that. There we go. And let's see what it wants us to do. So you can also use other apparatus that are usually available in a school lab. And complete the diagram to show a circuit you would use. Explain briefly how you would carry out the investigation. State the key variables that you would control. Draw a table with column headings to show how you would display your data. And explain how you would use your results to reach a conclusion. Let's briefly talk about what we're going to do. Here we go. We're being asked about the time taken to heat a beaker of water. You know what? Let's highlight it instead. Time taken to heat a beaker of water. And we're investigating the power produced and the time taken to heat the beaker of water. We've got a power equation here. So to my mind, it looks like we're going to want to record voltage and current, calculate power. And what else? Oh, look at this. Yeah, so time taken to heat a beaker of water. We're probably going to want to heat it between two temperatures and record the time it takes. Repeat for different voltages and different currents. Of course, we'll be changing the voltage, the current will change automatically. To repeat for different voltages and currents, we'll have to record them both so we can calculate the power, which is one of our key points up here. And then, once we've done a series of experiments, maybe we do it 5 times. So let's put that in there. But you want to do these things at least 5 times. So repeat for different voltage and currents, do it for 5 times, and then look at the shortest time to heat the water and compare that with the power. So probably draw a graph, I would guess, of power against time would do it. It's one way to do it, draw a graph of power against time, or you could calculate it out, the ratio from the table itself, and that will give you a result. But a nice little graph will give you a visual representation, so that's probably a good way to do it as well. Okay, let's start writing that down and see what we can do. There we go, so we've got power supply, let's put that in there. 0 to 12 volt supply. We'll just label that. Could we draw the supply any other way? Yeah, you can kind of draw it like this as well. Oops. There we are. So it's just a little bit like a normal battery pack, and then you put an arrow going through it. It's a variable DC power supply. I'm just going to leave it as this, so should be fine. We'll see how it works out. Okay, now we've got a DC power supply. We need to power the heater, and we want to record the current and the voltage across it. So let's bring it down here. There we go, a little ammeter. It's never a party without an ammeter. There we go. And straight down, I guess we'll just join that straight on there. Okay, now let's put in our voltmeter, and our voltmeter of course goes across the device we're measuring the voltage on, and the ammeter goes in the circuit itself. So there we are. So we want to control the start temperature of the water, and we'll do that by saying, let's say fill the beaker with 200 milliliters of water at 17 degrees Celsius. There we are, so we filled the beaker with water. Step 2. Let's see what we're going to do. We're going to turn on the heater. Oh, hang on a minute. How are we going to measure the temperature? We haven't got a single thermometer in there. Let's look at a diagram. We'll squeeze a thermometer in the side. And one thing I'll do is take off that alternate way to do the power supply for DC power supply. Let's get that there. Now, there we are. So the thermometer is now underneath the heater, being heated by the convection current. And let's label this clamp standard Boss. Thing you'd normally get in a lab. So step 2, we're going to want to turn on the heater and start the stopwatch at the same time. And of course we're also going to want to record the readings for the current and voltage. We'll do that in the table that we'll design. So we go, we're recording the readings for the current and voltage, and we'll do that in the table that we'll put in. Step 3, once the temperature of the water reaches, let's say 50 degrees C, or 57 degrees C, why not? We'll stop it and record the time. There we are, so then we're going to repeat the steps 1, 2, 3 for 5 separate readings of the voltage. We'll calculate the power in the table and then draw a graph. So there we are, we calculate the power for each situation in the table, and we plot a graph of power against time taken. And what we're looking for is the relationship between power and time taken. How does the time taken become smaller when compared with the power? Right, so the last thing to do is design the table we're going to put all the information into. And let's do that now. So what we want to do, of course, is record the voltage and the current and calculate the power. We can also put in the temperature rise if you want. The start and finish temperature is not really required because it's specified as part of the steps in the experiment itself. So let's just do that now. And there we go. So I've got the voltage V in volts, I've got current I in amps, I've got power which equals I times V in watts, and the time taken in seconds. And that should give us a nice set of results that we can then graph. Excellent. So hopefully you found that useful, hopefully that's helped a little bit. If it has, please feel free to like and subscribe, and have a great day.